Hello, class. The class rep, can somebody say something? Let me know if you're hearing me. One class rep or someone there, wants somebody amongst you say something to me. Hello?
Yes, ma'am, we can hear you.
Okay, that's good. All right, so you have to mute. All of you have to remain muted when we start the lecture. But when I want you to speak, when I ask questions, I want somebody to answer, I will, then you will just unmute and ask question when you want to. And also you can chat as well. So let's just give them more 3 minutes for others to join so we can start the lecture. So this lecture will be recorded just like Dr. Ogumbiade was doing for you. It will be recorded and then we will send it to you on LMS. So like the HOD said, this class is for biochemistry, chemistry, geosciences, chemistry education, medical lab, pharmacology, nursing, physiology, and physiotherapy. So I expect all students in those departments to be here. So please, those here, just notify your colleagues that is the same link that you use with Dr. Ogumbiade that you need to use here for me. So we'll just start the lecture now. So this section of CHM 121 that I'm taking here is Physical Chemistry 2, which is addressing solutions and solubilities. So at the end of the lecture, you'll have the notes. So we're looking at solutions and solubilities. So here we have a goal, what we want to achieve at the end of this lecture. At the end of this section of CHM 121, we expect you to be able to identify the solute and solvent in a solution. We also expect you to be able to define solution and know the different types of solution, such as saturated solution, unsaturated solution, and supersaturated solution. We expect you to also know what solutions of gases in liquids. You have an idea of solubility also. We expect you to be able to use solubility chart to determine maximum ratio of solute to solvent. We also expect you to know the factors that affect solubility. And such factors are temperature and pressure. And so at the end of this section of CHM 121, which is on solutions and solubilities, these are what you are expected to know. So let's go ahead. First of all, let's look at a mixture. You can stop me and ask questions. Let's look at a mixture. What is a mixture? A mixture is a combination of two or more materials that can be physically separated. Of course, it's not like a compound which has two or more materials but chemically combined. And so a compound which is chemically combined can only be separated chemically, but a mixture is physically combined and don't physically separated. So we have two key types of mixtures: the heterogeneous mixture and homogeneous mixture. So the heterogeneous mixture is the mixture in which you can see the different components separated. They're not homogeneously mixed. The mixture is having the composition is not uniform. In case of heterogeneous mixture, composition is not uniform throughout the mixture. So, and heterogeneous mixture it consists of more than one phase. It consists normally more than one phase. I'll talk to you about what a phase is. So, for instance, let me give you an example of an heterogeneous mixture. If you mix oil and water, mix them very well, they will not stay together. They will separate and you have oil phase and then the water phase. So the two phases, and that mixture is a heterogeneous mixture. Even the soup you cook at home, it's also heterogeneous because it's not a composition that is having the components evenly distributed. You have your vegetable, the solid here, the liquid here, the oil here, and so on. That's an heterogeneous mixture. But for homogeneous mixture, this is another mixture. Homogeneous mixture is the one in which all components blended together to look uniform. So, a homogeneous mixture is a single phase. It consists of a single phase. If it is liquid, it's liquid. If it is solid, it's solid. If it is gaseous, it's gaseous. So it consists only of a single phase. So this is a mixture in which the component or the composition is uniform throughout the mixture. So that's a homogeneous mixture. Now, let us look at solutions. What is a solution? A solution is a homogeneous mixture of solvent and solute molecules, homogeneously mixed, consistent, and uniform. So, like I mentioned, a solution is made up of two parts, the solute and the solvent. The solute is the dissolved substance in a solution. The solvent is a major component in a solution. So, like I mentioned before, in a solution, substances are physically combined because, a solution substances are physically combined, and so you can basically separate them. So you should know that. So I hope you understand so far. And also, in all solutions, like I said, a homogeneous mixture is, a solution is a homogeneous mixture. It can be gaseous, it can be liquid, it can be solid. I will show you some examples of gaseous solutions, liquid solutions, and solid solutions. So what is homogeneous mixture? That's a solution. And so in all solutions, whether gaseous, liquid, or solid, The substance present in the greatest amount is the solvent. And the substance or substances, it could be more than one substance, present in lesser amount are the solutes, which is now solvated in the solvent and gone into solution. So examples are here. Like I said, you can have liquid solution, you can have gaseous solution, and you can have solid solution. So here, example is soda. You should know soda water. So in this case, soda water consists of sugar, the solutes here are sugar and carbon dioxide. Sugar and carbon dioxide, and the solvent is water. You can see clearly that in that soda, water is a major component. That is the solvent. Other components just dissolve in it. That is a liquid solution. You have a gaseous solution, air. Air is a gaseous solution. You have the solute here, hydrogen, oxygen, and some other gases that could be present in air. But the solvent in this case is nitrogen, because nitrogen is present in a larger amount. Like you can see here, air has a composition of 78% nitrogen. As I told you before, that the component that is greater in the largest amount is the solvent, and the other ones are the solutes. So that is a gaseous solvent, where you have homogeneous mixture in constant composition, uniform. So, and then we have a solid solution. In this case, for instance, an 18-karat gold is a solution. 18-karat gold is a solution, and the solute here is nickel alloy. The solvent is gold. You have gold, 75% of gold, and then you have 25% of the alloy. So if you want to ask later, you can ask me, why is it 18 karat when it is 25%? If you need to ask that, you can ask later. But let's go on with our lecture. Now, like I mentioned to you when we started, that our goal is also for you to know the different types of solution: saturated solution, unsaturated solution, and super saturated solution. So a saturated solution is a solution that when no additional solid can be dissolved at a particular temperature. That means you have added the solute has gone into solution up to the extent that you can no longer add more solid. More solid can no longer dissolve in that solution. So it means that solution is saturated. Now, the unsaturated one is the one that is formed when more of the solute can still dissolve at a particular temperature. Note particular temperature, because at different temperatures, solubility differ. So when we're looking at a particular temperature, you now assess the saturation, unsaturation, and supersaturation at that same temperature. So the unsaturated solution is a solution that is formed, is a homogeneous solution that is formed when more of this solute can still be dissolved at that temperature in the solvent. So you can still add more. There's still space. It's not yet saturated. So you can still add more. The solvent can still take more solute. And the super saturated solution can form when more than equilibrium amount of solvent is dissolved at any given temperature. So in this case, it means you have excess solute in the solution. That means you have added, your solute has been taken in the solvent and is saturated. Then you still look for a way of creating a condition that can make that solvent take more solute than it's supposed to be as a saturated solution. So that means it's super saturated. And for you to be able to achieve super saturation, you have to increase temperature. You heat it up, because increase in temperature increases solubility. So for you to achieve that. So let's just look at the situation, how it is exactly. A saturated solution contains the maximum amount of solute that can dissolve. Don't forget, at a certain condition, certain temperature. So, and then that means the dissolved solute is there. There's an equilibrium between the solute and the system there, the solution. So the dissolved solute is there in solution, and you have extra, those ones that are undissolved, still there in the solution. In this case, if you can filter off the undissolved one and you still have your saturated solution. Then the unsaturated does not contain any extra solute that is remaining undissolved, because it doesn't even have enough. So it means there's still room for accommodation of more solute in an unsaturated solution. And then let's see a deeper, clearer explanation of a supersaturated solution here. Here we have these examples. We have the 3 beakers here. And that's figures 3.1 to 3.3. Each of them contain the same amount of solvent. So please, can you all mute? If you want to ask a question, maybe you can signify, or you allow me to complete before you ask any question. I will have time, I will complete on time and then give room for questions. So here, we have here 3 containers, let's say 3 beakers, having equal amount of water. In this case, water is the solvent. And then the figure 3.1 shows a beaker with more solid solute than in the saturated solution that is dissolving. So what do I mean by solid solute? Solid solute here is that what you're adding to your solvent is a solid that you're trying to dissolve in the solvent. A solid you take, in this case, let's say a salt. Who is talking? Please, can you mute yourself? So remain muted. So now, what do I mean by solid solute? What you're taking to dissolve is a solid you want to put in a solvent. Is when that solid dissolve in the solvent, that is, it becomes a solute. So the solute is the part of the particle that has dissolved in the solvent. So the solid, at a stage, you will see the difference between a solid and a solvent, a solid and a solute here as I go on in this supersaturated solution. So the solid solute, that is a solute that is formed, that is from a particular solid that goes into the solution. Now, the solute is the one that goes into solution. The solid is the one that you're trying to make to go into solution. It becomes solute once it goes into solution. So in figure 3.1, you see that more solid solute than can be in a saturated solution. So we have more. Like I mentioned to you before, a saturated solution have the solution and still have extra solutes inside of it, which you can filter off if you want to. So a super saturated solution now has the solution and is able to accommodate more solutes in it. So you have the solute, so the super saturated solution there, 3.1 figure. In figure 3.2, solid begins to crystallize as it slowly decreases the rate of dissolution. That means as you're adding your solid, the rate of the solution reduces because more solutes are going into solution. At a stage, the solution becomes saturated. So if you now continue adding more solid, the more you add, the slower the dissolution of the solid. So that is the second one. Then the last one shows that the solid becomes crystallized. It becomes hardened. That means as you continue to add, the solute that has already gone into solution is so much that it comes to the surface that as you add more solid, the solute in the solution could have contact with the solid at the surface that you're putting in and could adhere to it and then becomes hardened. And that is when you have what is called crystals. So now crystallization. Let's look at crystallization. As a solid solute dissolves in a solvent, I believe you understand what I mean by solid solute now. The one in solution is the solute. The one that is not gone into solution that you're trying to put in there is a solid that you have. So as a solid solute dissolves in a solvent, the concentration of solute particles in solution increases. As they keep on dissolving, more of them are going into solution, and so the concentration of the solute in the solution increases, thus increasing the chances of the solid particles colliding with the surface of the solid. So as you keep on adding, the solute dissolves in, and as the solute continue to increase in the solution, and as you continue adding the solid, then there's a greater chance that the solute particle will collide, will have contact with the solid that you're adding. So because of such a collision, the solute particle may become reattached to the solid that you're trying to add. This process is called crystallization. So when the rate of these opposing processes, that is this one solute trying to go into solution and then solute trying to come up to attach to the solid, those are the opposing processes. And these opposing processes become equal, then there is no further net increase in the amount of solute in the solution. That means you can no longer add, the solute can no longer go into solution. Instead, it's just coming here. So there's the two opposing processes become equal. So that is where you have what is called dynamic equilibrium is established between the solid going into solution and then the solid attaching to the solid. So that is where you have a dynamic equilibrium, where there's no net increase in the amount of solute going into solution. Still under crystallization, a solution that contains a greater amount of solute than that needed to form a saturated solution is supersaturated, as I've explained to you. So because the solution in a supersaturated solution, the solutes that are in the supersaturated solution is present in high concentration than the equilibrium concentration. The supersaturated solutions are unstable. They are unstable. You can go back and forth like reversing. So it's an unstable solution. So for crystallization to occur, the molecules or the ions of the solute must arrange themselves properly to form crystals. They must arrange themselves properly to form crystals. And so in a crystal, you have a proper regular arrangement of the ions of the solutes that are in that in the solution trying to form the crystal. So the addition of a small crystal of the solute is like a seed, provides templates for crystallization of the excess solute. So adding a little solute to what you already have becomes like a seed crystal that enhances crystallization, leading to a saturated solution in contact with excess solid. Like I've told you, when you have such, you have crystallization taking place. I told you we will finish on time, and then I'll give you time to ask questions. But before then, let me check and see if you understand what I meant by saturated, unsaturated, and supersaturated solution. In this case, I will want somebody to answer. Here, let's look at this situation here. At 40 degrees centigrade, the solubility of potassium bromide is 80 grams per 100 grams of water. Well, to make it clearer to you, before you answer this, let me explain to you what solubility is. How do you define solubility so that you understand better and be able to answer this? Solubility is the maximum amount of solute that can be dissolved in a specific amount of solvent, usually at a certain condition. Usually at a certain condition. Specific amount of a solute that can dissolve in a certain amount of solvent under a certain condition. For instance, like what you see here, I hope you're seeing the screen. The condition here is 40 degrees centigrade at that condition, that temperature. Now we're told that solubility of potassium bromide is 80 grams per 100 grams of water. 80 grams of potassium bromide per 100 grams of water. That means once you have 80 grams in 100 grams of water, that is, you have reached saturation. That is the apex of it. Nothing can go in again. No solute can go in again. So that is the specific amount that can dissolve in 100 grams of water in this case. So now, based on what I've explained to you now, look at scenarios A, B, and C, and somebody should be able to tell me whether A is saturated, unsaturated, or supersaturated, which of these different scenarios, which of them is saturated, which one is unsaturated, which one is supersaturated. Don't forget that the certain amount here of solvent, here the solvent is water, is 100 grams. That is the certain amount we're looking at. And then the solubility, that's the highest amount that can dissolve in that 100 grams, is 80 grams to make it saturated that you cannot put in anything again. So can somebody unmute and tell me, speak and tell us, let's see, A, B, and C, what do you think they are? And explain why.
A is unsaturated.
Hello.
Okay, yes. Speak.
Hey,
What's your name?
Is unsaturated.
A is unsaturated.
What is your name?
Ayomide ma.
Mojisola Moses.
I think who spoke first?
Me.
What's me? Who is me?
Ayomide ma.
Eh? What?
Ayomide.
Ayomide, okay. I want to.
Ayomide.
Ayomide, tell me. Difference
Yes,
of these three, what are they and why?
A is unsaturated ma.
Why? From what I explained to you, why do you think it's unsaturated? Moji, the other person, can you answer why?
Okay, ma. Hello, ma.
Yes.
The A is unsaturated.
Who is speaking?
Mojisola Moses.
Okay, Moji, okay. So A is unsaturated. Why?
There's still room for him to
Don't say
dissolve
you
more
feel.
solid.
Don't say you feel. Say exactly what it is that you're sure of what you're saying.
Yes, I said I still room to dissolve more solid in that A.
Okay, so what will it? Yes, you're right. But can somebody else? Let me pick another person.
Good morning, ma'am.
Ade, can you speak? Let other people.
Yes, you are right.
It's unsaturated, ma.
I want Ade to speak.
Good morning, ma.
Good morning. How are you?
I'm fine, thank you, ma. My name is Timothy. For A is because the maximum amount of solute that is required is not yet complete. The maximum amount is 80, but what we are giving for A is 60. So A can still take more solute, so it can be saturated, ma.
All right. Okay, you're right. So hold on. Let me pick another person that has raised hand. Was that was not Ade that spoke? Okay. Timothy. Okay, Timothy spoke. Okay, mute yourself.
Yes,
let Ade mute and answer the second one, B. Every other person should mute. Let only Ade unmute.
Hello, ma.
Hello.
Yes, ma.
Yes, Ade. What of the second one? B.
The second one is super saturated.
Why?
It's super saturated because there are 200 grams of solute. Meanwhile, we're giving 80 grams. So it will not contain up to that amount.
You're partially right. You're not completely right. Yes, it's super saturated. But you remember also that we're talking of a certain amount of solvent, specific amount of solvent. In this, in this case, when we're talking of solubility, we're always looking at finished water, was looking at 100 grams of water. So now explain on the basis of what I've told you now and justify why it's super saturated.
Sorry, ma, can you come in?
I say, if you look at, I gave you a definition of solubility, that it is the maximum amount of solute that can dissolve in a specific amount of solvent. In this case, when we're using water as solvent, we normally look at the specific amount of that solvent of water as 100 grams. So you have looked at it, you have said it's supersaturated, yes, but you did not explain it well. You told me it's 200 grams. I don't agree with you. So
okay, it's super saturated because the gram of water given in question is more than the maximum amount of solvent
Well, somehow, let me put it right again for you, although I'll still give you the answers and the next slide. We're looking at 100 grams of water. So if 200 grams of potassium bromide is in 200 grams of water, what of in 100 grams of water that we're looking at? That is solubility we're looking at. That means you have 100 grams of potassium bromide in 100 grams of water. We're talking of solubility is not just in any amount of solvent, in a specific amount of solvent. And as I explained to you that the specific amount of solvent, in this case, when we're looking at water, it's always 100 grams of water. So you base your solubility on 100 grams of water. So if I give you 1,000 grams of water here and give you maybe 300 grams of potassium bromide and ask if it is saturated or super saturated or what, you will not look at it and say, oh, because it's 300, so it's super saturated. No. What you look at also, you will look at the amount of water. So you will divide it that if 300 grams of, if it is 100 grams, how many grams of potassium, if you're given 300 grams in 1,000 of water, if it is 100 grams of water, how many grams of potassium bromide will be there? Then with that, you'll be able to judge. Maybe it will be only 30 grams or so. Then you will say supersaturated because you saw 200. No, it's not supersaturated because we're looking at saturation. We're looking at 100 grams of water. So let me get another person to answer the, Rokiba, you've been raising hand. Rokiba, can you answer the C? C? Rokiba? Is Rokiba there? Okay, if she's not there, James. Can James answer?
Yes, I'm here, ma.
Okay, answer the C.
Okay, so for the C, I would say it's unsaturated. And the reason why it's unsaturated is because if we're looking at the quantity of solvents or the amount of solvents given to us, if we're to equate it to this, it's going to be half of it. So for this particular solute to be soluble in this solvent, we need a minimum of 32.25. So because this is less than that, it makes it unsaturated.
You need a minimum of what?
32.5 or thereabout.
To add to this or what?
No, not to add to this, like to be the exact solute to make
to
this
80
to
grams.
be soluble in this solvent.
Okay, so now, as you see here, 25 grams, sorry, I didn't put grams, I'll put it before I send it to you. 25 grams of potassium bromide.
Yes.
In 50 grams of water.
Yes.
So that means it will be 50 grams of potassium bromide in 100 grams of water.
Yes.
So that explanation is more simple, it's clearer. So you see 50 grams is not up to 80 to make it saturated. So it means this one can still accommodate more solute. So this one is also unsaturated, just like A is also unsaturated. So in this, we don't have a saturated solution here. We have unsaturated and supersaturated. A and B are unsaturated, but A and C are unsaturated. B is supersaturated. So, so you can see here, this is what we just did now. Look at it here. So the condition there is 40 degrees centigrade. And so number 1 is saturated, 2 is unsaturated, 3 is supersaturated. I'm not talking of A, B, and C. So if we code saturated as 1 and code unsaturated as 2 and code supersaturated as 3. So A is 2. A is unsaturated, and it has less than 80 grams in 100 grams of water. So if we look at B, same as 200 grams of potassium bromide in 200 grams of water is the same as 100 grams of potassium bromide in 100 grams of water. So we see that this is higher than what is supposed to be. So it's greater than its solubility. And so that is supersaturated. Saturated is just the same as the solubility. So, and then the C here is also 2, unsaturated. So as a, that is a, sorry, there's a mistake there. Did you notice the mistake there? 50, supposed to be 50. Supposed to be 50, so I'll correct that one for you as well. So that is what it should be. And I think with this little exercise, everybody, sorry, I wasn't able to call everyone that lifted hand. So with this exercise, I believe you understand very well what saturation, unsaturation, and supersaturation is. Let me complete this lecture so that I can give people opportunity to ask questions. So forms of solution. We say solution, a solute does not have to be in the same physical state as a solvent. I know you can agree with this, with me on this, because when we look at like that potassium bromide and water, you could have your solute to be in solid form, and then the solvent to be in liquid form. So they don't have to be in the same physical state. But the physical state of the solvent usually determines the state of the solution. Like I've told you that we can have liquid solution, that means the solvent is a liquid. We can have gaseous solution, that means the solvent is a gas. We can have solid solution, that means the solvent is a solid, like I explained to you before. So what determines the state of the solution is the physical, is the solvent. So as long as the solute and solvent combine to give homogeneous solution, the solute is said to be soluble in the solvent. It's said to be soluble in the solvent as far as it is already inside that solution. It has combined to form a homogeneous solution. So let's see. Let's see here some forms of solution. Gas in gas solution. Like I gave you an example before of air. Air is gas in gas solution. So we have nitrogen, oxygen, argon, and so on. But the solvent there, like I mentioned to you, is nitrogen because that's the one that is present in the highest concentration, highest amount. So we can also have gas in liquid, where you have like the carbonated water I mentioned before. You have sugar, it's one of the solutes, and you have carbon dioxide as a solute also. But water is the one that is more, like you're drinking almost water, you're just adding a little sugar and a little carbon dioxide. If you look at your carbonated water, you will not be able to say that I see gas somewhere alone, separate there as a different phase, and then liquid here as a different phase. It's so mixed, blended, such that you see water, you see liquid. So that is a gas in liquid solution. We also have gas in solid. Gas in solid, example is hydrogen and palladium metal. The palladium metal is the solvent, because that is the one that is more. Hydrogen is also there, but it will blend so much that you will see solid, that there's hydrogen inside it. So the state of the, that's what we mean by the state of the solvent is what determines the state of the solution. So you also have liquid in liquid, where you have like gasoline mixture, petroleum, you have all of them. In this one, it's a polar issue, polarity. If it is a polar solution, it mixes in another polar solvent. So if it is polar and non-polar, they don't mix. Like I described to you, the situation with oil and water. Those are, water is polar and oil is non-polar, so they will not mix. And so they form different phases, which makes it homogeneous mixture, a heterogeneous mixture. A heterogeneous mixture is not a solution. So for you to have a homogeneous mixture, for you to have a solution, liquid in liquid, the two liquids have to be of similar polarity. You can mix alcohol in water and it will become like a solution. You can mix, so that's how it is. Then you have liquid in solid. You have liquid in solid. Then this is, the example is dental amalgam, mercury in silver. Mercury, you know how it is, like a liquid, but you know, silver solid. So, but silver in this case is the solvent. So mercury is the solute. And so what you will see a solid solution. You have solid in liquid. This is the kind of the potassium bromide we talked of, and the kind of sodium chloride, the salt and the sugar, all those ones are solid in liquid. You just add and then it goes into solution. The solute goes in, dissolves. So that is solid in liquid. Of course, water is a solvent, which is the one of the highest amount. We have solid in solid, metal alloys, like example I gave you before of gold. You have the alloy, nickel alloy, that is of lower percentage, and gold that is of higher percentage. And so gold is the solvent, and this is another example here that is given to you. So this is what we have for you today. And in case you have a question to ask, I will take questions. I will take questions. So I can't see anybody raising hand. If you understand, okay, and raise hand to talk. Okay, Balogun, Ayomide. Ayomide Balogun, you can speak. Unmute yourself and speak. Unmute and speak. Ayomide. Okay, Obinna. Okay, no, I've taken you before. You've spoken before. Let Gafar, Okikiola, Gafar, I want you to speak if you have questions.
Yes, ma'am.
Okay.
In the gas and solid solution, when you said the palladium metal, the hydrogen gas doesn't really show. Does it mean that the solution is homogeneous, ma'am?
Yes, it's homogeneous. Every solution is a homogeneous mixture. That is, you cannot differentiate between one and another. It's not separated out. Everything is in constant uniform. So everything is in constant, in regular uniform. Yes, composition is uniform, uniformly arranged and mixed and blended. So you cannot separate it out. So it's a solution. So all the solutions I've stated here, the different kinds of solutions, any of them, you will not be able to pick something out that, oh, I've seen something that is different here. You will not be able to pick it out. They're evenly and constantly, all the compositions are evenly and constantly distributed. Yes,
my
yes,
question.
okay.
Okay. You said that the solute does not have to be in the same physical state as the solvent, but the physical state of the solvent usually determines the state of the solution. I don't understand that sentence, ma.
Okay, I will still use this slide to explain it.
Okay, ma.
So if you look at, let me take the one I say gas in liquid. You know the two of them are not in the same state. This is gaseous state, this is
Okay.
liquid state. So
Yes, ma.
now gas in liquid, gas is a solute that is in liquid, in the solvent. The solvent
Okay.
is water. And you know solvent, water, the solvent here is a liquid.
Yes.
So gas is going into the solvent. So it's the solvent that determines what state of that solution it will be. So because what the solvent here is liquid, if you put solid in it, you put gas in it, put whatever you put in it, as far as it forms a solution, it's going to be a liquid solution, a liquid solution.
Okay.
You understand now?
Okay.
That is why we
Yes,
say
ma.
that it's the solvent that determines the state of the solution.
Okay. Thank you, ma. Thank
Okay.
you, ma.
So who else has I think I picked Obina. Joseph. Joseph, you have a question? Joseph. If Joseph is not there, Omawumi, can you ask?
Good morning, ma.
Good morning.
Ma, you mentioned earlier that when the solution reaches dynamic equilibrium, that's the point where the formation of crystals equals, the rate of formation of crystals equals the rate of the solute going into solution. Ma, at that point, can we say the solution is saturated?
Yes, it's saturated. It's saturated, and yes, that's saturated.
Okay.
Yes.
And would raising the temperature make those crystals go into solution?
You know, when you get the crystals and super saturated, it's saturated and you add more, raise the temperature to add more. And then it will take more of the, when you raise the temperature to be able to add more, it will take more of the solute. Like I explained that when it takes more of the solute now, what now happens is now at the surface between the solid itself that has not gone into solute and then the solute that has gone into solution. So the solute in a saturated solution will come up. And now when you add more, the solute will be able to have contact with the solid. So at a stage, when that equilibrium now is established between the solute going into solution and solute going to touch the solid. That is a state at where the crystals form.
So at that state, the
At that
solution
state, yes,
is
where there's
saturated.
no, yes, that is where you have the dynamic equilibrium. That is that stage where you have the contact between the solute and the solid. Then the solute then tends to, because it's in collision with the solid that is trying to come in, the solid is trying to come in, but it's already saturated. So that solution is already saturated. And so that exposes the solute to have contact with the solid. And then having contact with the solid, it adheres back.
All right.
That is the opposing force, adhering back to the solid and also going to solution. So that is where you have that opposing forces. That is that stage that you have the crystallization.
All right, ma. Thank you.
Okay. Many questions. Let me see who has not asked. Fortune. Fortune, can you ask?
Good morning, ma'am.
Good morning.
Yes, ma'am. I wanted to ask a question regarding solid in liquid. The example under there, that's seawater. Okay, is it a colloidal solution? Because there's sol and gel. I don't know. That sol is solid dispersed in liquid. So this particular seawater now, is it a colloidal solution?
The colloidal solution, and this is a pure homogeneous solution with the solute completely dissolved in the solvent. When you have colloidal solution, you will have certain particle sizes. Then you talk of some particle sizes in the solution. So this one is not.
Okay, so okay, so that means that since you said that the solvent is what gives the state of the solution, like if it is liquid, it's going to be liquid. So does that mean now that if we have a colloidal solution now, we can still say that it is going to still be liquid if it is solid in liquid?
It's a solution. Once it's whatever name you call the solution, once it is a solution, it's a solution. It will still take the form. You will call it after what the solvent is.
Okay, ma. Thank you, ma.
All right. So another, let me see who has not. Agbebomi, Precious.
Good morning, ma.
Good morning, how are you?
I'm fine, Mama. I want to ask, is it possible for us to have a solid solvent?
Yes, I've shown you example here.
Yes, but I do not understand how, if we have a liquid solute and a solid solvent, how is the solvent going to dissolve the solute, or is the solute going to dissolve the solvent?
Is the whatever is solvent, you say solid, did you say solid solvent?
Yes.
Okay, and we have example here of mercury in silver. So what it means is that the one that will, how do I put it, consume the other one. The one that consumes the other one is the solvent. So, and it will remain, the state of that solution will remain the state of that solvent. So if the solid consumes the liquid, it means you have a solid solution. But if it was the liquid that was more, it means the one that is more is the one that consumes the other one. So if it was the liquid that was more, and then you bring the solid to add, if the solid doesn't melt in that solution, it doesn't melt in that solvent, that you're not getting a solution. That is an homogeneous mixture. No, that's a heterogeneous mixture. You're not getting a solution. So if you bring the solid to go into the other, a small amount of solid to go into a large amount of liquid, it will not be a solution because it's a heterogeneous mixture if it cannot dissolve. A solution is when you have one thing completely dissolving in the other one. So the solid or completely consumed and blended, the regular uniform composition in the other one. Do you understand?
Ma. Yes, ma, I do. Thank you, ma.
All right. I want to take another one before we go. Who else? Ayomide.
Ma, I was the one that I've already asked my question, ma.
Okay,
I asked that.
I still saw your
The
hand
solid does not
lifted up. Okay, now Timothy,
Okay.
your hand is still lifted up.
Good morning, ma.
Good morning.
Yes, ma'am. A situation will have chalk particles added to water. We observe that the chalk particles do not dissolve evenly in the water. So can we say in that case that we are having heterogeneous mixture or suspension?
Yes, you have said it. It's a suspension, or it could be, yes, suspension could be. That's how it is. Yes, the particles are there. It's not a solution. A solution you will not see anything that is different from the solvent. Yes, a solution. It will still look like the solvent, but it's having a mixture, something else mixed in it for a solution. So that one will be a suspension. It's not a solution. Solution is just even distribution. You cannot see the difference between the solvent and the solute. Okay, is that okay? So who is still lifting hand, because we will have to, I saw 3 hands still lifted. Whose hands are those ones? Okay, I think Obina, you've already spoken. Timothy. And Joseph, have you spoken? Okay, so we'll bring this class to a close now, and we will send the lecture to you on LMS, what's been recorded. Thank you, and encourage the rest to be in the class like you have done today. So try and be in the class on Wednesday. Use the same link like the HOD told you. All right, thank you. Bye.
Bye, ma.
Bye.
Bye.
Bye-bye.
Yeah.
Thank you, ma.
Thank you.
Bye.
Yeah.
Bye.
Bye.
Thank you, ma.
Thank you. Bye.
Thank you, ma.
Yes, thank you.
Bye, ma.
Mark, bye. Samuel.
Bye, babe.
Bye. Yes, Mark, bye.
Bye, ma. Thank you, ma.
Balogun. Yeah.
Bye.
Aisha. Bye.
Bye, ma.
Amy, yes, bye. Akimbiyi, bye-bye. Obinna, bye.
Bye.
Yeah,
Bye, ma.
bye-bye.